Welcome to The Explainer. Look, I've spent years in the trenches of high-stakes backend architecture, and today we're digging into a topic I am incredibly passionate about. We're talking about PostgreSQL, and specifically what senior engineers know that most developers just don't. We're going to completely tear down the illusion that your local development environment is anything like a live, breathing production database at scale. Seriously, if you've ever had a query run flawlessly on your laptop, only to absolutely incinerate your servers at 3 in the morning, this explainer is built exactly for you. We're going to explore the high-stakes database secrets, the brutal scalability trade-offs, and the systemic bottlenecks that top-tier engineers navigate every single day to keep systems alive. Let's get into it.
To really understand how a senior engineer approaches a database, we first have to look at how they approach code in general. I absolutely love this quote. Senior developers don't write better code. They delete more of it. See, I've watched this happen so many times. A junior developer joins a team, gets super excited, and proudly adds 50,000 lines of new code. We're talking new ORM wrappers, incredibly complex abstractions, elaborate eager failover systems, the whole shebang. But a senior engineer, they come in and systematically delete 15,000 lines to remove hidden architectural liabilities. They know through hard-earned experience that every single line of code and every single unnecessary database query is a literal liability just waiting to break under load.
Okay, let's dive into Section 1, the senior engineering mindset, moving from reactive to systemic. Before we even get into the technical weeds, we really have to address the psychology of incident response. Take a look at this comparison. When production suddenly slows to a crawl, the junior instinct is almost always purely reactive. They panic, they restart the Kubernetes pod, they massively scale up the database instance, and they essentially cross their fingers hoping the problem goes away. They're just treating a symptom. The senior approach, on the other hand, is completely diagnostic and systemic. They ignore the noisy, flashing alerts. Instead, they look for specific decision tree signals to actually find and fix the underlying architectural flaw. Because the hard truth is, you simply cannot safely accelerate a system that you don't understand. Moving right along to Section 2, Mastering Database Indexing Strategy, the Anatomy of Fast Queries. So if you don't understand how different indexing strategies actually work under the hood, you will waste hours, maybe days, blindly tuning queries. You have several specific tools at your disposal here. Hash indexes, for example, use a hash table and give you those blazing fast O1 lookups, but they are absolutely useless if you need to do range queries or sorting. That's exactly why the B tree is your default workhorse. It easily handles equality, range queries, and sorting using a highly balanced tree structure. But as your application grows and queries get more complex, you'll inevitably need composite indexes, which span across multiple columns. And let me tell you, these require extreme care. This brings us to what might be the most important rule of indexing, the leftmost prefix rule. When you build a composite index, your database optimizer reads that index from left to right. If you get your column order wrong here, the database will completely ignore your beautifully crafted index and just do a full table scan anyway. So always put your equality conditions first. Boom, right at the front. Next, you place your highest selectivity columns. Those are the ones that filter out the absolute highest number of rows. And finally, you save your range filters, like greater than, less than, or between, for the absolute last position in the index. And this brilliantly illustrates the ultimate goal we are chasing with all of this, the covering index. Think about it. If your index contains every single column that your select query is asking for, the database can perform what's called an index-only scan. That means it completely bypasses reading the actual table pages from the physical disk. By eliminating that heavy I/O disk pressure, you drastically reduce latency. It is pretty much a magic bullet for read-heavy workloads. Which leads us directly into Section 3, killing the N+1 problem, the silent performance killer. Now, perfect database indexes will absolutely not save you if your application code is secretly destroying the network. Let's break down the math of an architectural disaster, usually caused by lazy loading ORMs. You write what looks like clean, elegant, object-oriented code locally, just asking for a simple list of 100 users. Cool, that's one query. But then your code loops through those users to fetch their posts. Without you realizing it, your application silently fires off an individual query for every single user. What literally looked like one clean line of code on your screen just generated 101 separate network round trips. 54x. I really want to emphasize this number to show you the scale of this problem. In a typical production environment, that N+1 approach we just talked about might take roughly 88 milliseconds.
entirely due to the massive network tax of those 101 round trips. But if you switch to an eager loaded join, meaning you fetch all the data upfront in a single optimized query, that execution time drops to about 15 milliseconds. You are getting a 54 times performance improvement simply by spotting and fixing the N+1 problem. It's wild.
All right, Section 4, Surviving Production Database Migrations, when production burns down at 3 a.m. So your queries are incredibly fast now. That's great. But eventually, you're going to have to change your schema. And surviving a live production data migration with tens of millions of rows is exactly what separates the juniors from the seniors. A junior might just write a script that mixes schema changes right alongside a massive update statement hitting a million rows. We call this a bad migration. Why? Because it heavily locks the table, exhausts your undo logs, and ultimately crashes the app. The senior practice is entirely decoupled. You instantly make the schema change, the DDL, and then, completely separately, you use non-blocking background workers to backfill that data in small, safe chunks. And if you are lucky enough to be using PostgreSQL, you have access to a feature that DevOps engineers literally consider a holy grail: transactional DDL. This amazing feature allows you to wrap your scary schema changes, like an alter table, inside a standard transactional block. So if your migration randomly fails halfway through for some reason, the database automatically rolls back the entire schema change. It's like an undo button. You never, ever get stuck in a corrupted, half-finished state like you absolutely would in older, non-transactional database engines. Let's zoom out for our final segment. Section 5, Architecting for Systemic Scale, Designing for Slowness and Failure. See, high-performance backends aren't just about writing fast queries. They are about orchestrating complex, distributed systems where hardware inevitably fails. Now, what's really interesting about this slide is how it builds on the famous CAP theorem. We have the Passelcy theorem. It dictates that even when your system is operating perfectly, with absolutely no network partitions, you still have to make a brutal, unavoidable architectural trade-off. You have to ask, do we want ultra-low latency, or do we want perfectly accurate, strongly consistent data? Because you simply cannot have both. You have to design for the specific latency budget that your business actually requires. So, to protect your system from tribal knowledge and all these hidden bottlenecks we've talked about, you need hardcore, battle-tested guardrails. Here is a rapid-fire checklist every senior engineer implements. First, rigidly enforce separate schema and data migrations in your CI pipeline. Second, and this is huge, never, ever perform a network call inside a database transaction block. Doing that creates an idle in transaction state, which is literally the #1 silent killer of Postgres performance. Third, enforce automated connection leak detection using try with resources. And finally, please stop autoscaling based on CPU usage. It is a lagging indicator. You need to scale based on concurrent in-flight requests so you can catch the load spike before it destroys your latency. Which brings us to the ultimate test of your backend architecture. I want to leave you with this provocative question, and I really want you to think about it. If your database fails right now, at this exact second, do you know exactly what your system will do? Will it gracefully degrade and keep serving users, or will a localized failure cascade into a total, catastrophic, systemic outage? Don't wait until 3 a.m. on a Saturday to find out. Take these strategies, go audit your own backend today. And hey, if you found this explainer valuable, share it with your engineering team, start implementing these guardrails, and go optimize those queries.